Welcome to a new episode of AI Research Radar, where we showcase the most cutting-edge developments in the field of artificial intelligence. Join us as we shine a spotlight on the latest advancements and breakthroughs in AI research. From machine learning to natural language processing, AI Research Radar covers it all to keep you informed on the forefront of AI innovation. The paper titled, Linearity of Relation Decoding in Transformer Language Models, presents a novel method for understanding how transformer language models, LLMs, encode and decode relational knowledge. The authors propose that much of the knowledge in LLMs can be expressed in terms of relations, focusing on a subset of relations that can be approximated by a single linear transformation on the subject representation, referred to as a linear relational embedding, LRE. The methodology involves several steps. Identifying relations. The authors identify various relations in the language models, including factual, common sense, and linguistic relations. They also pinpoint cases where the LM predictions accurately capture relational knowledge, but this knowledge is not linearly encoded in their representations. Constructing linear relation representations. The authors construct linear relation representations by creating a first-order approximation to the LM from a single prompt. They argue that these representations exist for a variety of relations. Evaluating LREs. The authors evaluate the faithfulness and causality of the LREs. Faithfulness measures how well the LREs predict the transformer output for different relations. Causality measures whether the LREs can causally influence the LM's predictions. Finding and validating LREs. The authors propose a method for finding LREs and validating their effectiveness. They hypothesize that the computation of the LM can be well approximated by a linear projection, which can be obtained from a local derivative of the LM. Applying the LREs. The authors apply the LREs to create an attribute lens, a novel probing method that provides a view into a LM's knowledge of an attribute of a subject with respect to a relation. The LRE is an affine function that maps any subject representation in the domain of the relation to the corresponding object representation. In LMs, the inputs to these implicit LREs are hidden representations of subjects at intermediate layers, and their outputs are hidden representations at late layers that can be decoded to distributions over next tokens. The authors find that for a variety of relations, the decoding procedure is approximately affine, LRE, and these affine transformations can be computed directly from the LM Jacobian on a prompt expressing the relation. The attribute lens is a tool that the authors developed to visualize the object token distribution at each layer for a given relation. This tool allows the authors to see where and when the LM finishes retrieving knowledge about a specific relation and can reveal the presence of knowledge about attributes even when that knowledge does not reach the output. The experimental work is designed to validate the use of linear relation representations, LREs, in transformer language models, LMs. The authors conduct experiments on 3 different language models, GPT-J, GPT-2, XL, and Llama 13B, using a manually curated dataset of 47 relations spanning 4 categories: factual associations, common sense knowledge, implicit biases, and linguistic knowledge. Experimental setup. Models. The authors study autoregressive language models, primarily focusing on GPT-J, with additional results for GPT-2, XL, and Llama 13B included in the appendix. Dataset. The dataset consists of 47 relations across 4 categories. Each relation is associated with a number of example subject-object pairs, as well as a prompt template that leads the language model to predict object when subject is filled in. Experiments. Linearity of relation decoding. The authors first investigate whether LREs accurately predict the transformer output for different relations, that is, how faithful they are. They find that for a variety of relations, transformer LMs decode relational knowledge directly from subject-entity representations. Causality of LREs. The authors then test whether the LREs causally influence LM predictions. They use the inverse of LRE to change the LM's predicted object for a given subject. They find that when an LRE causally influences the LM's predictions, it is also faithful to the model. Location of LREs in the network. The authors also investigate where in the network the representations exhibit LREs. They find that there are considerable differences in LRE faithfulness when estimated from different layers. Application of LREs. Finally, the authors apply the LRE to create a novel probing method they call an attribute lens. This method provides a view into a LM's knowledge of an attribute of a subject with respect to a relation R. They find that the attribute lens can identify cases where an LM outputs a falsehood that contradicts the LM's own internal knowledge about a subject. In conclusion, the experimental work in the paper involves testing the LREs on a variety of relations and language models, investigating their faithfulness and causality, and applying them to create a novel probing method. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled, Fewer is More, Boosting LLM Reasoning with Reinforced Context Pruning, introduces a new method called CoT influx, which aims to enhance the mathematical reasoning abilities of large language models, LLMs. This method is a two-step pruner that first selects essential chain of thoughts, COT, examples, and then prunes unnecessary tokens to fit within the LLM's context window. The authors propose the creation of a math reasoning dataset, MRD3, using GPT-4 and EVOL Instruct. This dataset includes problems of varying difficulty and reasoning steps, which allows CoT influx to generalize across a broad range of math problems. The problem is formulated as an optimization problem, with the goal of optimizing the input to the LLM so that it can correctly answer the question while keeping the token count of the input within the LLM context window limit. The pruner module is a two-stage policy network that first selects the most helpful COT examples and then removes unimportant tokens from these selected examples. The pruner treats the target LLM as a black box and serves as a plug-and-play module for LLMs. The authors propose a multi-objective reward function and use reinforcement learning to train the pruner module. The reward function measures the LLM loss, FEWSHOT math reasoning effectiveness, and token length constraints. A pilot study was conducted to observe the impact of adding more COT examples on LLM reasoning performance. The results showed that adding more COT examples improves LLM reasoning accuracy, but the limited LLM context window hinders the full potential of FEWSHOT COT learning. The authors also propose a novel training approach with reinforcement learning to mitigate the gradient issue. They design a reward function to measure the LLM loss, FEWSHOT math reasoning effectiveness, and token length constraints. Then, they design a difficulty-aware data loader filtering appropriate problems and introduce two techniques to stabilize the RL training. The authors of the paper conducted a comprehensive set of experiments to validate the effectiveness of their proposed method, CoT influx, in enhancing the mathematical reasoning capabilities of large language models, LLMs. The experimental setup involved the use of several LLMs, namely Llama 2-7b, Llama 2-13b, and Llama 2-70b. The authors evaluated the performance of these models on 5 different math datasets: GSM-8K, ADSUB, Multiarith, SVAMP, and SingLeak. The metric used to measure performance was the exact match, EM, accuracy of the predicted answers. In order to establish a benchmark for their results, the authors compared CoT influx with several baseline methods. These included COT and FEWSHOT COT prompting, prompt retrieval, and prompt compression. The results of the experiment showed that CoT influx significantly outperformed all baselines, achieving an absolute improvement of 1.36% to 14.09% over state-of-the-art baselines. Notably, Llama 2-70b with CoT influx surpassed the performance of a broad range of larger LLMs and even outperformed GPT 3.5 by 2.5% on the GSM-8K dataset. The authors also conducted an ablation study to understand the contribution of each component of CoT influx. The results indicated that removing any pruning stage decreases performance, with the removal of token-only pruning causing a larger accuracy drop than shot-only pruning. This suggests that shot-level redundancy is easier for the pruner to learn. Finally, a sensitivity analysis was performed on the hyperparameters to investigate the robustness of CoT influx. The authors found that the training of the CoT influx pruner is highly robust as long as the token target is not overly aggressive. In conclusion, the experimental work conducted by the authors provides strong evidence for the effectiveness of CoT influx in improving the mathematical reasoning capabilities of LLMs. This is AI Research Radar. Now, we will be delving into the next paper on our agenda. The paper titled MED-FLAMINGO, a multimodal medical FEWSHOT learner, presents the development and evaluation of MED-FLAMINGO, a model for medical visual question answering tasks. The methods used in this study can be categorized into three main stages: data collection and preparation, model pre-training, and evaluation. Data collection and preparation. The authors used two types of datasets for pre-training MED-FLAMINGO: the MTB, interleaved dataset, and the PMCOA, paired dataset. The MTB dataset was constructed from 4,721 textbooks from various medical specialties, resulting in approximately 0.8 M images and 584 M tokens. The PMCOA dataset, on the other hand, is a biomedical dataset with 1.6 M image caption pairs collected from PubMed Central's open access subset. Model pre-training. The pre-training of MED-FLAMINGO started with the OpenFlamingo 9B model checkpoint. This model is a general domain vision language model, VLM, built on top of the frozen language model Llama 7B and frozen vision encoder clip VIT/L14. The model was trained using Deep Speed 0 Stage 2, which shards optimizer states and gradients across devices. The model was pre-trained for 2,700 steps, or 6.75 days in-wall time, including the validation steps, using 50 gradient accumulation steps and a per-device batch size of 1, resulting in a total batch size of 400. Evaluation. The experimental work conducted to validate the methods was comprehensive and multifaceted. The process began with data preparation, where two types of datasets were prepared for pre-training MED-FLAMINGO. The first was the MTB, medical textbooks, dataset, constructed from 4,721 textbooks from various medical specialties. The dataset consists of approximately 0.8 M images and 584 M tokens. The second dataset used was the PMCOA, a biomedical dataset with 1.6 M image caption pairs collected from PubMed Central's open access subset. The next step was model training. The authors utilized 8x80 GB NVIDIA A100 GPUs for multi-GPU training. The model was trained using Deep Speed 0 Stage 2, which shards optimizer states and gradients across devices. The training process lasted for 2,700 steps, equivalent to 6.75 days in-wall time. The authors then evaluated MED-FLAMINGO on generative medical visual question answering (VQA) tasks. They designed a new evaluation protocol to measure the clinical usefulness of the model generations. This involved an in-depth human evaluation study with clinical experts. The evaluation used two existing VQA datasets, VQAR80 and PathVQA, and a new one, Visual USMLE, a challenging generative VQA dataset of complex USMLE-style problems. Human evaluation was also implemented using a Streamlit app. Clinical experts were asked to rate the quality of the generated answers with scores from 0 to 10. For each VQA problem, the raters were provided with the image, the question, the correct answer, and a set of blinded generations that appear in randomized order. Finally, the authors performed deduplication and leakage based upon pairwise similarity between images from their pre-training datasets and the images from their evaluation benchmarks. They embedded the images using Google's Vision Transformer, preserving the last hidden state as the resultant embedding. They then found the k-nearest neighbors to each evaluation image from amongst the pre-training images. They sorted and visualized image-image pairs by least Euclidean distance and found that images might be duplicates until a pairwise distance of around 80. Beyond this point, there were no duplicates. This detailed experimental work provides a robust validation of the methods proposed in the paper. Thank you for joining us for this episode of AI Research Radar. Be sure to stay tuned for our next episode where we will showcase the latest innovations in AI research. If you enjoyed the content, please consider subscribing and liking the video.